So I can give a bit of a background. So I spoke with most of you before the talk, because this can be a very long talk that no one wants to hear entirely, right? So I'm going to tailor it to the audience by skipping most of the pieces that I think will not be interesting, right? So what happened is that SUI, so the blockchain, started now about a year ago, its mainnet, the 3rd of May. So we just got its first anniversary, right? And it has been running with a consensus core called Narwhal and Bullshark, right? And it has been running actually surprisingly well, in the sense that it has no blackouts, no liveness failure for an entire year. Usually you have a little bit of hiccup, right? We didn't, right? So what do you do in these conditions? You change it over. Exactly. So we are going to entirely replace the consensus core of the blockchain. This is hitting mainnet, testnet this week. And if all goes well, mainnets toward the end of June, right?
Can you remind us the size? How many nodes do you have on the?
About 100, about 100 nodes. I'll present a little bit of the scope, like in the first slide. So yeah, I'll just ask 4 quick questions to further tailor the talk, right? You all know what blockchains are here. That's obvious. Byzantine fault tolerance, it's obvious as well. Okay, DAG-based consensus, you've heard about, or do you? Okay. And Narwhal Bullshark, no, okay, perfect. Okay, that I suspect. So I'm going to give you a bit of the context, right? So the way that SUI works, and that is not going to change, right, for an exception, right, is we run proof of stake, lots of nodes, right, a priori, and then we would select about 100, right? So there is a special rule, a percentage of stake that you need to have, a minimum number of nodes that we wish to have. It's 117, last time I checked, a few days ago, right? So they form, for the duration of an entire day, 24 hours, a Byzantine quorum system. So 12 plus 1 nodes are honest at all time, right? We should be performant well and working under nice conditions if up to 1/3 of them are malicious and behave arbitrarily, right? So 12 plus 1 is very familiar. Yes, perfect, right? GST, does it rings a bell? Okay, perfect. So the protocol is partially synchronous, like the Bullshark version that we implemented. If you read the paper of Bullshark, I may not recommend it. The original one had an asynchronous fallback, right? No one ever implemented that thing, right? Bullshark, for all practical means, was also partially synchronous. So I'll skip all of these introduction. And today I was planning to focus about the ordering layer of Mysticeti, the new consensus core, right? But I mean, I have this question a lot. We do also other things in the blockchain. So node selection algorithms are there. Node committee reconfiguration do happen every day, right? Transaction execution, we do execute transaction, right? There are financial incentives. There is a programming language. It is a smart contract platform, right? It's just that I can chat about them if you like after the talk, but not out.
The community configuration means you said there are 117 nodes.
Mm-hmm.
And all of them participate.
Yes. And after a day, we rerun proof of stake and we see if they're going to remain for the next day, right? Usually they do, right? But if they're very bad, they may not, right? Or they may change line of business as well, right? We don't really know about that. So, yeah, what we had here is I'm trying to explain the protocol with a Lamport diagram. So are those familiar, or is the first time you see? Okay, perfect, right? So quite standard. I get that question a lot. I'm presenting with 4 nodes. It does not mean we run with 4 nodes, right? It's just examples. So times goes toward the right. Squares are the messages. Little arrows like these are messages sent, right? And every line represents what one node does, right? And so here is how it works. I'm going to give you a very brief overview of the engineering mechanism. So, and then tell you a little bit of a story about why we did such thing and why it took such a long time. So a node, so a validator, what does it do? It collects users' transactions. Eventually, it has enough user transactions or a timeout is triggered, at which point it decides to create a block. This is the yellow thing you see there. So it sticks a round number, very familiar. Most consensus protocols do that. Its name, it signs it, and that's the base structure of the block. Now there is a twist. And the twist is we add 12 plus 1 links to blocks of the previous rounds. If you're familiar with DAG-based consensus, this is perfectly normal. If you come from hotstuff or PBFT, this may be like a shocking, right? So now, in this example, you see 3 links, right? 12 plus 1, right? That again is the structure of the block. And what happens as well is from time to time, we have predefined leaders, right? Very known, there is no notion of secret election, right? They are derived from the public parameters. And we know exactly when they're going to happen. So for instance, here we have node 1 being the leader of round 1, right? Everybody knows it ahead of time, derived from the public parameters, right? And so if you are at round 2 and about to create a block, you make a special effort to include the block from the leader among your links here, right? Special effort means you wait a bit longer, right? We can come to that later. That is where the partial synchrony actually comes from. And finally, every node does that in parallel. Again, quite normal if you're familiar with DAG-based consensus, and again, quite shocking if you come from linear chain protocols, right? And eventually, you have a DAG that looks like this, right? So, and here is now a bit of the story, right?
The column, the blocks in the column, they have to be all the same, or it could be different?
No. Every block in a column will contain a different payload.
Ah, well.
Yeah.
But they could be overlaps.
They could be overlaps. Yes. Yeah. Yeah, absolutely. So why did we end up having such simple structure? Let's say just blocks that were linked. If you're familiar with other blockchain DAG-based protocol, you may remember DAGs that are more complex than that, right? They would require every vertex to be a certificate rather than just a block. And that simplifies your life a lot when it comes to running a consensus on top of it. Well, so here is basically the story, right? It was about 2 years ago. And at the very beginning, there were not many engineers at Mysten Labs, right? Mostly George and myself spend quality time implementing Bullshark and making it production ready. Among that quality time, we realized that new engineers would come and get onboarded, right? And then there were multiple message types, quite some complexity in implementing votes for Bullshark that are very small messages that needs to be propagated very fast compared to headers or batches that are larger and that would require different optimization for the network layer. And then one day we had a conversation and we realized that now that we've been all passed on doing research, right? What happens if our engineers, actually if even 3 of those engineers change career and go work somewhere else? Well, we realized that we will be back spending quality time maintaining the code base, right? So we thought this is unsustainable, right? Maintaining actually a variety of message types on a consensus core that is way more complex than what it looks like. On paper, it was all very simple. You would just have, even in the case of hot stuff, you send a header, you get votes, you have a certificate, may look like a QC, you send it back and that is it. Actually, it was never that simple, right? Small messages would require sometimes dedicated TCP channels to be sent. Otherwise, they would erase access to the NIC, which compared to larger messages. Then you find yourself yielding between those different threads to make sure that there is a fair access. And then you realize that it doesn't work on all the payloads that you may have, right? So it was very complicated at the end, and we had a lot of lines of code, way more than the prototypes, to maintain those systems. And one day we said, okay, now we need to simplify things and have a single message type. It may make consensus more complex, algorithmically speaking, but now we can say that these, which we explain in 3 slides, right? It's mostly, let's say 99% of the engineering complexity. Here you have networking, here you have your message propagation layers, you have access to storage, you have most of your memory storage interface that happen here. And that thing here will take actually 99% of the time of the engineering team to maintain, implement, make sure that it remains up to date, right? By not having to care about anything else. So, and now is the question. We have such DAG, right? Way simpler. Can we do 2 things? First, achieve a very low latency. because now we have a lot of round and a lot of messages, right, between, let's say, traditional leaders, right? And second, build a consensus protocol that is as efficient as the previous one, right? That took us a year, but I think we can finally, right? Yes?
That protocols already have just one type of message?
No, they mostly don't. Actually, I would say none do, right? Usually you do have a notion of votes, right? And a notion of certificates. And when you see a DAG, you see vertices. Usually every vertex is a certificate and the result of a consistent broadcast. Right? That is usually what you say.
Wait, so the problem you're saying with bullshit was it's a systems problem.
It's a purely system problem. I would say even it's a purely engineering problem.
What I'm not sure I understand the issue. So do you have message types?
Yes.
The message type is just the first couple of bytes of message. So why does it matter if you have more message types?
Because we had some messages that were big, other messages that were small, and that would need to be propagated in different ways and handled in different way by the core, basically.
You can hear all the messages are the same size.
Yes, mostly the same size, and if not, at the very least, they are all blocks. So a single node does not need to worry about sending in parallel very small vote messages to help other validators, and choose if it needs to prioritize that or its own message propagations. Right? That was like a purely engineering problem that required a lot of line of codes, basically. Weird mutexes all over the place. Very scary.
A problem you wouldn't know about until you.
Exactly. So, and we implemented a prototype for a while. We've been quite proud of that prototype, right? And then when we went to production, the problem appeared effectively, right? So yeah. It got solved, right? It was fine for a year, right? But it's just that maintaining it is very, very consuming.
Even with 100 nodes, this is a problem.
It is a problem. Yeah, yeah. It's it was a lot of lines of code. Mostly this was the problem, not really the number of nodes, right? So simplifying the engineering layer was what we've been trying to do, and what has been asked actually for a while from the engineering team as well, right?
Mm-hmm.
So this was the original motivation. Also, we needed to cut down the latency. And one other thing that we needed to do, and we can see that in a bit, was that we realized that in a year of running the protocol, we observed exactly 0 Byzantine attacks. And we observed weekly crash faults, right? There are always like, let's call them professionals that sometimes forget to turn on their nodes, right? So across updates, right? That happens, right? And so it seems a bit a sad story that to handle crash faults in the same way as Byzantine faults, we would give up so much performance, right? So we thought, look, if they are crash faults and benign, can we support them without impacting performance, right? And of course, we should tolerate Byzantine faults as everybody else, right? That's perfectly obvious, right? So you'll see, actually, it is quite simple, strangely enough, right? So, yeah.
So how bad was the impact if you like do not optimize for different message types?
It was not bad at all if you were running under good conditions. And then as soon as you were having network jitters or validators that were very popular with respect to others, then everything started happening, like very, very weird problems. You would have like performance drop of up to 50%, right? For no obvious reasons, right? And then when you run your profilers, you realize that sure, adding a bit of a delay here would have fixed it. And eventually we did that, right? We had like 2 pages long of configuration parameters, right? To fix all of it, right? Yeah. So I said a bit of the motivation, right? And here there is one that I can emphasize from our discussion, which is about signatures, right? So we had that joke running where we said, look, we have built like Bullshark, we built the biggest BLS verifier, right? Because our CPU time was mostly about verifying signatures. So smart contracts were fairly naive, right? It's the beginning of this era, let's call it that way, right? And so, yeah, verifying BLS signature for every DAG certificate in Bullshark was quite demanding, right? So we thought, can we get away with no certificates at all? So there is no notion of having to aggregate any signature anymore. And we actually reduced on the overall protocol the number of signatures. So that helped with CPU.
Still BLS?
It is today BLS, yes, right, but it may change basically back to 825.519. Yeah, because there is no notion of aggregation anymore, right? So that is, yeah, that is a little bit of the catch, right? So yeah.
And threshold doesn't help.
Now there is no need to thresholdize. Indeed, when you build the following DAG, there are no certificates happening anymore. While before, every vertex was a threshold BLS. Right now it's not, right? So yeah, basically that helps. And now what do we do once we have the DAG? We are going to observe specific patterns over the DAG and deduce commits or skips, non-commits, based on what the patterns look like. And so those are the two main patterns that we observe. So as we said, all the engineering complexity was about building the DAG, right? And now what happens is that we have one module, right, that runs the consensus that is quite simple. It does not have write access to the storage, does not handle networking, does not send any message. It just interprets the DAG that is already in memory or in storage and looks for these two patterns. So the green one, we call it a certificate pattern, and the red one, we call it a blame pattern. I'm going to remember to remind it where later on, when we get close to using them and combining them in a variety of forms, but that's about the only thing we do, interpreting the following patterns. If you're familiar with hot stuff, and PBFT, you may realize that this pattern looks like a hot stuff certificate if you interpret the middle round here as votes for a leader, right? So we actually have done two protocols, two ways to interpret the various patterns, right? One to get a consensus protocol, the one that we have in testnet and the one that I'm planning to present today, but we have another one, a more crazy one, that basically allow you to interpret slightly different patterns in slightly different ways, to forego consensus and allow you to immediately finalize some types of transactions, right? We can leave it for another day, unless you're interested, right? And we're not planning to put it into production yet, but in a few more months it can change, right? So that's why I'm focusing on the consensus.
This is not FastPay, this is something else.
So it's a bit of FastPay flattened into the DAG, basically, right? So
You have the one DAG that we do both.
Exactly. So you interpret FastPay runs over the DAG. We don't send extra FastPay messages, basically. Yeah.
Sorry, the previous round you had the previous graphic was like leader in round 1 and then in round 4.
Yeah.
And then in the next slide, you're saying every round has a leader.
Yes. I'll come to that later. Otherwise, you're going to steal my thunder.
Okay.
Yes. Yeah. So Mysticeti, the consensus protocol, right? So we focused on all these DAG protocols on ordering leaders, right? I get that question sometimes. So just to be clear, right? We would like to have as end goal, as an example, all honest node agreeing that we first output leader 1, then leader 4, then leader 7 in this example. And why don't we care about all the other certificates? Because if you're familiar with DAG-based consensus, you know, right? It's fairly simple to then output a total order for all the other blocks, right? You simply look at the causal history of L4 in this case, and you flatten it however you like, through whatever arbitrary rule. If you're familiar with DAG-based consensus, it's traditional. They all look like that. They all operate like that. If you only know hot stuff, this may be like mind-blowing again, right? We did not invent that, right? So what do you do as a validator once you have the following DAG in your memory? So the first thing you do mentally again, right? You divide it into waves. That's again in your head, right? There is nothing special that is about it. You put stickers on your block if you like, right? And we're going to say that each wave lasts for 3 rounds. So wave 1 would get round 1, round 2, round 3, and then we continue like that, 3 round by 3, right? Step number 1. So again, all in the head of the validator, right? Once it has the following DAG as an example. Then second thing it does is that it takes the public parameters and it uses them to derive in a deterministic way the leader for every first round of every wave, right? So we can stick a little bit of a name for those familiar with hot stuff. Propose, vote, certify. If you're not familiar with those, it doesn't matter, but you're familiar with that, it may help you see why we do such thing. But we simply say, look, every round of, every first round of a wave gets a leader in a deterministic fashion. Nothing special there. Again, you just interpret, right? Then what we do is we say, okay, we have that. Let's shift all this mental image of the DAG by one round and repeat. Now we pretend that the DAG starts at round 2, not anymore at round 1. And we do the exact same thing. We assign waves. So round 2, round 3, round 4 are part of the blue wave, right? R5, R6, R7 are the rounds of the second blue waves. And again, they get a leader for every first round of the wave, right? And then we do it one last time, right? So you don't see it well with the transparency here. There is a hole in the DAG that may happen because validators crash recover. Sometimes they're just malicious. We never know, right? We can have a leader spot assigned to a missing block, right? It's perfectly normal. It's fine, right? So that is how we get one leader per round. We interpret, let's say, 3 times the same consensus protocol shifted by 1, right? And then we do the same shift horizontally, we can say. And we can have more than 1 leader per round, right? So they're ranked. So ranked A, leader 1A, is a higher rank than 1B, which is higher than C and higher than D, right? Purely deterministic again, right? So this is fine. We can have all these leaders. We can have a protocol to commit all these leaders. It will work independent on the number of leaders. But for practical reasons, we are going to restrict ourselves to 2 leaders, right? After some experiments, right? I'm telling you why in a bit, right? We realized that having a small constant number of leaders, regardless of the number of nodes, about 2 to 3, maybe 5, right? But certainly not like 12 plus 1, is actually good for performance. You'll see why in a bit. And now I'm taking an example. I think it's actually this DAG to explain the commit rule. It will look very familiar if you know hot stuff, and slightly less if you have a bull shark in your head, I would say. So the idea is, I'll first give you an overview of the rule, right? It's not designed to make you understand exactly how it works, because then we have a crafted step-by-step example with 6 rounds that gets, let's say, all the corner cases, right? And we can work them out together. So again, we only do that by observing the following patterns, right? That's the reminder of the slides that we had before. Okay, so here is what happened. Here is how we reach consensus. So once you have the following DAG in your head, you start from the highest round and you start to identify, if you can, 12 plus 1 blame patterns. So this is an example. So in this particular example, L4A has 12 plus 1 blame patterns. Yeah?
So the blade pattern is just a missing link?
It's just a missing link to the leader. Yes. Yeah. And if that happens, we are going to color red the specific leader. Okay. If that doesn't work, we search for 12 plus 1 certificate patterns. Same patterns as before. This is an example. So each one of the green blocks of round 6 actually defines a certificate pattern over L4B. If we have 12 plus 1 of them, we label green to commit leader L4B. So this is the direct decision rule. And it can happen that we don't observe like any of those patterns, right? So this is an example, right? This is a very unfortunate example, right? We don't have enough blames. We don't have enough certificates, right? L2B managed to send its block to what? 2 validators, and that's about it, right? In that case, we cannot do anything with the direct decision rule. And then we use the fallback rule called the indirect decision rule. And here I think is where we may differ a bit from traditional DAG-based consensus. So the indirect decision rule has 2 steps. The first step is to look for an anchor. So the anchor, by the rule, says it's the first leader you encounter after your wave. So the first leader that as the after round 3 in this case, that is either already marked as to commit or that is marked as undecided. So it cannot be marked as skip. So in this case, again, it's a very particular case. L4A would have been the natural anchor, but unfortunately, it is already marked as skip, so it cannot be the anchor. Then we go for the next one, and L4B is the anchor of L1P. Okay. Again, it's an overview of the rule. Like I see a lot of perturbed faces. Don't worry, it's going to be much clearer, like in a bit, right? That's step number 1. Step number 2 is you search for a link, if your anchor is commit, between your anchor to your leader. Right? That link needs to go through a certificate pattern. So again, it's the same pattern that we keep observing, right? Look at this. We have an anchor. We have its own leader. The anchor is labeled as to commit. There is a certificate pattern over the leader, and there is a link between the anchor and the certificate pattern. If that happens, we can mark L1B, the leader, as to commit. If not, we mark it as skip. Seems a bit of a magic. You'll see in a second why and how it works. Right?
In practice, is this easy to decide?
It's easy to decide, yes, yes. I'll now run through an example and I'll point out which cases are very common, and we do observe them all the time, which one are extremely corner cases that may even require malicious behavior and interaction to happen, right? And then how we fix them or how we tolerate it.
And generally, it's a very dense graph. That's why it's inclusive.
Yes, exactly. Yes, it's very dense and also it's very small because this protocol. So now we take the following example. It has like 6 rounds. In practice, since it's quite efficient, we rerun the protocol every time we learn about a new block. So usually we only have to go through 1 to 2 rounds, right? If you crash recover, you may need to go through more, but it's not a hard thing to do.
Wait, so this is quadratic in the number of nodes, or what?
It is quadratic in the number of nodes, yes.
That's
Well, 100 nodes, maximum a few rounds to go through. I mean, it's not great axiomatically, right?
Okay.
But
the Ethereum guy would say you have any kind of 1,000 nodes, then what are you gonna do?
if you have that, I think you have bigger problems. I think you cannot even build the DAG if you have 1,000 nodes that go, right? These protocols, this BFT quorum system, regardless of DAG based or hot stuff, do not go more than.
You go to community style.
Yeah. I mean, I spend quality time running and implementing those things. Never managed to go above 200 nodes and be consistent with performance, right? We start like, you realize that you start paying for bigger and bigger machines just to go to 150 nodes, right? And then at that point, it becomes like a bit weird because the machine costs like a house, right? So this is a bit of the example, right? So the first thing you do as a node, so you run your DAG protocol, that's all good, right? This again is going to be maintained by the engineering team. Let's say we don't care about it anymore, right? Now, what we do maintain and do care, let's say ourselves, the research team, is the algorithm that is going to interpret it, right? So this algorithm is going to do one step before beginning. It's going to label all the leaders as undecided. Okay, now it's going to try to decide them all. So you'll see this is a particular unfortunate example. You'll see why. So first thing we do is to say, look, those 2 rounds here in that example are part of unfinished waves, right? So this round R5 defines leaders part of a blue wave that is unfinished, and L6A is a leader of a pink wave that is unfinished as well. So we cannot decide them at this stage. So we ignore them. We leave them as undecided. And now we start from the latest leader that we have. So in this example, L4B, we go backward, right? If this could be obvious, again, depending on your familiarity with similar protocols. If not, it's not a problem. You'll see later. I'll point you out when this becomes actually quite obvious. So L4B, what do we do? As before, first thing is we try to apply the direct decision rule. Direct decision rule says, let's try to look for 12+1 certificate patterns or 12+1 blame patterns. In this case, we have 12+1 certificate patterns. This is the case we observe 99% of the time. So if we are after GST, the network is good, propagation goes well. At round 5, these nodes, actually all these nodes, would wait a bit longer to include L4A and L4B. So if they can, right? So there is no reason why, if the network is in a beautiful way, synchronous, let's say at this time, you would not observe this pattern. If that happens, it's really good, right? You will see these allow us to commit very, very quickly. So this is the first thing we do. So L4B is labeled as to commit. At this time, we don't output anything. We just label our own edges. Then we go for L4A, right? And L4A is a different example. And here is how we tolerate crash faults. So L4A has 2f+1 blame patterns and can immediately be labeled as to commit. It's not stalling the pipeline and is not blocking anything. So here, the inside, it may seem quite obvious now, is that if L4A is crashed, benignly crashed, not adversarially, just the machine is down or is going through a protocol upgrade, which actually takes quite some time, it turns out, well, no block from round 5 will ever link to L4A. It will be impossible for L4A to ever have a certificate at that point. And so being able to immediately label it as a block that will be skipped immediately gives you crash robustness, let's say, for free, effectively, right? We don't need to treat Byzantine fault in the same way as crash fault, and we don't even need to know if a Byzantine fault looks like a crash fault, right? We just do that immediately. And then we can continue. L3B is the next one. L3B, I think, is not a particular example. It's pretty nice. L3B has more than 2f+1 certificate patterns. It has 3f+1 certificate patterns. And so here we can have like another little bit of a story, right? So are you familiar with protocols like Ziziva, for instance, that have a very optimistic fast path, right? In the case where you manage to have signatures or approval from the entire committee, 3f+1, you can go extremely fast, right? So we were intrigued by those for a while, I would say since 2020, right? To observe, is it even possible to have 3f+1 in a very lucky scenario, like 3f+1 support for a single leader? Well, it's not. Actually, you never see that in practice, right? And why is it so? Well, it turns out that, at least in our case, about 60 to 80% of node operators are professionals. So they have their node with a very good uptime all the time. They're very well connected. They actually pay for their network, which means that they live in a synchronous network, right, in practice, right? And we have 20% of people who have different interests in life. And so those people, right, effectively always prevents you from getting to that scenario. So when you weight by stake all of these protocols, you realize that getting 100% of the stake is just not happening. So it's sad, but now we know. So super optimistic fast path may not be like the best use of your time in these type of systems, at least.
What you're describing is like you get 2.5f+1.
Exactly, right? Or yeah, something like that. Like
That's not enough. That's not enough for a fast path.
if the super fast path of Ziziva, etc., requires 100%, right? So even if you get 99, is not enough, basically. So yeah, 100% we don't see. Yes.
So just one clarification. So here, you would go like L4A is your first priority leader, and then that gets a blame, so you go to L4B.
Yes,
Even if that doesn't work, you go to L3.
exactly. You'll see that in a bit why we have multiple leaders. But you're completely right, because intuitively, if you have your transaction that is embedded in a non-leader block, you may need to wait up to 1 round before getting it committed. So if you have multiple leaders per round, you have more transactions that are committed upfront within three blocks, basically, right? So that's a bit of the idea. Then L2, yeah, then there is like L3A that is missing, right? This is the same as any DAG-based consensus protocol. If a leader is missing, there is no vertex, you just ignore it and you proceed with the next one. Again, this is shocking if you come from PPFT because that triggers the most horrible of all protocols, the view change, right? And here there is none of it. Not our contribution, same for most DAG-based consensus protocols. So L2B. L2B is the extremely unfortunate scenario. So in that particular case, it did require a combination of bad luck and probably either network asynchrony or Byzantine behavior. So we have that scenario. So not enough votes, let's say, links to have a certificate pattern, not enough to have a blame pattern either, a completely missing block at round 3 that is not even able to help us decide one way or another. And so that means the direct decision rule fails. But worse than that, we now apply indirect decision rule. So remember, step number 1, finding the anchor. The anchor is the first block after your wave, first leader after your wave, so L5A. It's also undecided, right? So this is a completely combination of bad luck, right? L2B may even happen from time to time, we never know, but having your anchor also undecided at this stage is also quite unlucky. So if this happens, L2B cannot be decided at this stage. You will see why this is bad later. It's bad for performance. And we need to skip. We need to go with L2A, and we'll come back to that later. Essentially, that's what it means. So L2A is a traditional example, right? So, I mean, not traditional, but in this case, 2F+1 certificates, all good. We label it as green. To commit is fine. And now we have an interesting case, L1B. So L1B managed to get one certificate pattern, but not more than that, and not enough blame patterns to be directly skipped. So the direct decision rule also fails. This pattern, we can observe it from time to time. This is not necessarily extremely bad luck. This can happen. It basically means that L1B was a bit late or a bit big, which means it becomes a bit late, right? So it does not have 2F+1 certificate patterns. It has usually a little bit less, right? So that happens, we apply the direct commit rule, the indirect decision rule that comes to help us, right? That's the same as before. So what you do, step 1, you look for an anchor, have a look at the first leader after your wave, L4A, but this one is already labeled as skipped. Remember, we labeled it before as skipped, right? So it cannot be an anchor. Remember the rule. The anchor needs to be either undecided or already labeled as to commit. So this is the anchor. So that was step 1, the indirect decision rule, finding your anchor. Now that you have your anchor, you look for a certificate pattern that links the leader to its anchor. And usually we are going to have it, right? So why are we going to have it? We're going to have it because if you have enough of these certificates patterns, even if you don't have all the 2F+1 to use the direct decision rule, chances are that next blocks, basically, from round 4, will link to at least one of your certificate patterns, right? So that may happen. In that case, we're good. We're just going to label as to commits L1B, not immediately, but fast enough, let's say, right? And then we have the last case scenario, L1A. L1A is also quite unfortunate. I would say almost as unfortunate as L2B, but it may happen if, let's say, the nodes 2 there puts a bit of bad will, right, to make that appear, right? So it sends its proposal to only half of the network, right? So half of the network would link to it, but that is not enough to have even a single certificate pattern, and we don't have enough blame patterns. We need 2F+1 to label it as skip, right? So again, direct decision rule failed. We go through the indirect decision rule. Step 1, finding your anchor, well, is the same as before. Why is the same as before? Because all blocks of a given round have the same anchor, basically, right? So first leader out of your wave would have been L4A. It is marked as skipped, same as before. L4B is your anchor. Now we look for a certificate pattern and we don't find one. And that is okay. We can then label L1B as to skip. And so now what happens is that we have run a protocol that seemed complicated and that gave a color to our DAC, right? We have we could mark some as to skip, some as to commit, and this very unfortunate one that we'll see in a moment, right? So these protocol like seem complicated, but it basically requires read access to your storage. Actually, most of the time we keep the recent DAG in memory, so you don't even touch your storage. CPU consumption is actually quite low because you don't load all the transactions. You just operate over smaller headers, like abstractions over the blocks here, and you don't have networking involved in any sense. So it's actually quite efficient, even if it took like 10 slides to explain it, right? That fits in one Rust module. It's not more complicated than that, right? And we're happy to maintain it. It's feasible to maintain it while doing research in your life, right? Instead, as opposed as a reliability engineering, right?
So I just want to make sure I understand this. Each line basically represents a signature by the previous block, right?
No, it's just a hash link.
This is the hash.
Just a hash link.
No, so where are signatures here?
Every time that we create a block,
Oh,
we sign it. That's the only users.
and then the next block hash links to it, and
Yes.
just verifies signature.
Yes, yes. I did not mention that it's exactly like that. So every time that you want to hash link to a block is the same as virtually every consensus protocol. You do verify that it's correctly signed, you do verify that it's currently formed, and you do verify that if it references a payload that is not immediately available, you need to make sure that you already downloaded or that you have a proof of availability. That is the same for like, all BFT consensus protocols, I would say. Yeah, I should have said it, absolutely. Yeah. So yeah, this is the role of signature in the system, basically.
Wait, so each node is verifying 2f+1 signatures.
Yes. Yeah, but over very different messages.
Very different data.
Yeah.
So wait, it's speed up so you can still patch it.
Maybe we should. Right now we call 82519 batch verify function, which is basically just a more efficient way to verify 82519 signature, not through cryptographic means. I think it uses some like hardware instruction. Right. That's
Wait, you said you use BLS today.
so these implementation, we have it in two ways. We have it in BLS in production, and we have our research initial prototype that is 82519, basically. Yeah, it's unclear if we are going to maintain BLS in production. Yeah, because we maintain both libraries today. We maintain this fast crypto library that has both implementations, basically. Yep.
There's no reliable broadcast for each block, right?
No.
Just send.
Just send, yeah.
Somebody equivocates.
You will see. It's not an issue if someone equivocates, right? Intuitively, it's not an issue because you will never observe two certificate patterns for conflicting blocks. But we will come to that later, right? Yeah.
One thing I was confused about is the pipeline waves.
Yes.
How do you like order the comments?
That is the next slide. Yes. So here we just have colored our edges, right? Now we need to output a total order. It's actually quite simple. So what we do is we take them in order from L1A to L4B. That is step one. We call it the leader sequence. And now we need to cut the leader sequence upon encountering the first undecided block. So here you see why it was such an unfortunate example, the one we have here. Because should this one be decided, even as skipped through a crash fault, we would have been committing all of these at once, immediately, right? But since we have been blocked so early in the pipeline, we need to wait and find out L2B. It will eventually be decided either as skipped or as to commit, right? This is the liveness proof. I'll give an intuition later that basically says that L2B will eventually be decided, right? But again, that's unfortunate. Like we could have gone all the way through, right? And now you see why we don't want to have too many leaders per round, right? Because imagine the more leader per rounds we have, the higher the chances are to encounter in an early stage of the pipeline one L2B basically that blocks everything out, right? So two are good because then if your original leader crashes, you still save the round by having the backup leader. Three are also good. Yeah.
Your point earlier was that you check like for something undecided, you check the round like R+2.
Yeah. Next way. Yeah.
What if you're missing both of those? Do you check like R+3 or is it?
So
Like what if L5A and L5B were both wrong?
We're missing, you mean?
Yeah.
You cannot do anything.
So we just mark these stays on set.
Yeah, I mean, here, if you have both that are missing, and you know that a missing block that you don't have yet is, so if a missing block would be a leader specifically, right? You cannot do anything until you reach 12 plus 1 in the next round. Yeah, because it's an undecided one, right? If you can move on, eventually they'll become as skipped and you'll be good. Right, so that's a bit of a, yeah, the reason. So we have to cut the pipeline very early. So we have L1A, L1B, and L2A. So we can remove everything that was labeled as skipped, right? That is actually why we labeled them as skipped. And then we are left with those two. And what we do is the same thing as every DAG-based consensus protocol. So we start with the first. We realize that it has no causal history. So we output it to the application layer. And then we look for L2A. It has a causal history. And so we use whatever deterministic rule to order little one and little two, because little three was L1B already output. This is very classic. All DAG-based consensus protocol do that as well. So for instance, we would go for one and then little two. Whatever deterministic rule happens, that is fine. And that is our output sequence. So once we run the protocol, this is what we can commit at this stage. Those are the blocks that we could commit. Let me see how we are on time. We have like 5 more minutes, right? Yeah, exactly. So, okay. Okay, in that case, I will focus on our discussion later. So about a weird incentive protocol that we have that is fairly unproven. Safety is proven, liveness is proven, and nothing else about fairness is proven. So how do we do to avoid L2B as scenarios as L2Bs, right? So we realized that we would like to remove or avoid slow leaders, so unreliable people, as much as we can, right? And so we have a very simple protocol, right? So it works like that. Every 5 minutes, every 300 rounds, we look back at what we committed. So in this particular example, we run a very long consensus protocol for a while, and we take a look at L7, and we look for round 1 from L7, everything that we committed. That is everything that is green in this example. And now we're going to attribute a reputation score for every node, right? Based exclusively on that subdag. So let's start with node 1. We're going to give it 1 cookie point every time that it managed to have a link for a leader given the green subdag. So in this example, it has 3 points because at round 2, it linked to itself being a leader at round 1. At round 3, it linked to the leader L2. And at round 6, it linked to the leader L5, right? So 3 points for node 1. Node 2, similar thing, but note here, we are quite unfortunate. We can only give it 4 points, although we had like five links in total, simply because the red link here is not part of the committed subdag. Namely, this particular block could be seen by some nodes, but not by others. So it does not count regarding its point. We need to make sure that every node who observes the green subdag will attribute the same score to every other node, right? And we do the same thing for node 3, and we do the same thing for node 4. And now we say, look, we take the top performing nodes, and we say, all right, you guys are going to be elected as leader, so we're going to bias the leader election algorithm more often, right? So instead of saying you're simply weighted by stake, the more stake you have, the more chances you have to be a leader, the number of links that you have in the DAG, right, the number of points you have, are going to give you a higher probability of getting in. That improves latency by 30%. By removing stragglers. So now, is this algorithm safe? We think it is. Is it live? We think it is. Are there weird incentive games that you can play to exclude others, include yourself? Namely, your paper where you had nodes that were making blackmailing each other to include votes to other people's proposals. All of these may apply. So these runs in production as well. So if it's a bad idea, we would appreciate.
But there are block rewards in this, right?
They are block reward, but they're not based on you being a leader.
Oh. So what are they based on?
Simply you being in the committee, actually.
Oh.
Yeah.
So there's no incentive to do.
There's no incentive to be a leader, nor a special role to be a leader. Now there are external incentives to be a leader because I guess you have a little bit, maybe a little bit of an advantage. Again, it's a DAG-based consensus. So every time you commit at the very least 12 plus 1 other blocks. So your MEV advantage and power of discretion is quite low because you are going to have your transaction mixed up with your immediate sub-DAG, right? So you need to,
The sub-DAG, they're mostly overlapping, right?
they could be overlapping, yes. Now, they usually don't contain all the same transactions, so. Right.
The differences are minor. Might be a couple of.
No, the similarities are minor.
Oh, is that right?
Yeah, the similarities are minor. You really require a bad user to spam all the nodes and fill the mempool of everybody else, right?
So there's no gossip network.
No,
Ah,
no.
I see.
Yeah.
I see.
So yeah,
So you just send your transaction to one of you.
exactly.
Uh-huh.
Yeah. Yeah. So that is most of it. Yes,
So this incentivizes you to wait for the leader, like before you publish your block.
as
Right.
well. Yes.
It doesn't incentivize you from just not publishing, right?
No, doesn't.
And that doesn't seem to be a problem. Like I can imagine like somebody just wants to gain their reputation and just like that, like if it's, you know,
Well,
if it's not my turn, if it's not my turn to be leader, I just don't bother publishing.
yes, but then remember that you get your cookie points by publishing a block that eventually gets committed and that links to a leader. So you still need to create your block.
I create my block when I'm linking to it when I see the leader. Oh, I guess sure.
Right.
Yeah.
Right. So intuitively, this is not perfect, but I've been asking that question to many people that have interest in, let's say, crypto economics. So is there something obviously wrong? No one could tell me, yes, there is that, it's obviously wrong, right? So I guess if you find anything.
Wait, but the wrong would be just an ABV style attack? Or-
Yeah, for instance, like a very bad way of gaming that system that would make it extremely unfair for whatever definition of fairness, right? We only thought about safety and life for these particular subproducts. Yeah. I don't know if it's interesting, but it's what we did. Yes.
That's a separate point from this, but if you kind of like fit into this schema VID type architecture, would this be like a kind of like, or how do you say?
Horizontally
Horizontal
scalable.
scale?
Yes. We planned to do it, but it would add engineering complexity. So we said simplest thing, and if there is a need, we will one day.
I see. So currently, if I'm linking a block, like including hash, I need to download its data, but in the future, maybe I just download a small portion of it.
Exactly, but I hope that this future would not come, right? Yes, but yes, yeah, we could scale that way. Yes,
Are these blocks limited in size? Or is it?
they are limited in size. I don't remember about what, but what I do remember is that we never hit the maximum size. So we deployed these. So we have like preliminary like scientific benchmarks like that are only with small networks. And compared to Bullshark, we are much better in terms of throughput and latency, right? I mean, we need to run more experiments to have like better graphs, right? They're expensive, right? So that's why we waited for the latest iteration of the code before going for it. All of these throughput gain is because of simpler engineering, right? No, nothing else. There is no protocol reason why we should get a better throughput than Bullshark, right? Just simpler engineering allowed for a variety of optimization. Latency is gained by the multiple leaders and the cheaper CPU load, right? Then when you ask your engineering team to run benchmark, they don't give you a graph. They give you this, and they say, look, run the thing for 24 hours, and it did not crash. So it's actually not a bad way, right? What they said is they took the maximum load that they ever observed on the chain, they multiplied it by like, I don't know, like 5 or 4, and they submitted that load for like an entire day, and they observed P50, P95, and that's how it compares to the current or previous version of the protocol. So we do see an improvement there as well.